We are interested in obtaining tight bounds on the factorial of n, specifically in the Stirling approximation. So the bounds are given by these terms. So the upper bound, it has this term square root of 2 pi n, then n to the n e to the minus n, and the same terms appear in the lower bound. The bounds, the lower and upper bounds, they differ in this factor here. So here we have exponential 1 over 12n. Here it's exponential 1 over 12n plus 1. And these bounds are valid for any positive integer n. How can we prove something like this? So the first step is sort of like to have loose bounds, a loose lower bound and a loose upper bound. And the trick, is the common trick of relating a summation to an integral. The idea here is that the factorial is a product. So by applying the logarithm, we convert the product into a sum. Okay, so we will basically handle the factorial n, and then we take the natural logarithm. And so this will be the summation k from 1 to n of log k. So this is log 1 plus log 2 plus log 3 and so on. And log 1, of course, is equal to 0. So here, this is log 1, which is 0. This is log 2. This is log 3. This is log 4, and so on. And the curve passing through these points is the curve log x. Now, to obtain a lower bound, as is clear from the figure, the integral of log x from 1 to n will give us a lower bound, because the logarithm of the factorial of n is this area. So a lower bound will be the integral of log x from 1 to n. Doing integration by parts, we will get the lower bound as n log n minus n plus 1. If we are interested in an upper bound, then we can use this shifted logarithmic curve. So this is log x plus 1. So now when x is equal to 0, we have log 1, which is 0. So this is a curve that goes through the origin. And the area under the curve now from 0 to n will be an upper bound. Again, doing integration by parts, this will give us the upper bound n plus 1 log n minus n. So we have those bounds. So this is the logarithm of factorial n. And, this is the upper bound. This is the lower bound. If we basically exponentiate the three sides, we will get that the factorial of n is living between n to the n, e to the minus n. And the upper bound is n plus 1 to the n plus 1, e to the minus n. And note that e to the minus n is a factor that appears in Stirling's approximation. Also, we have n to the n. Here it's n plus 1 to the n plus 1, but n to the n, it is here and there. Okay, and here we have e, which is not here. So this is, sometimes actually those bounds are enough for whatever we are doing, but in other cases we really need tight bounds. So these bounds can inspire us like to construct tighter bounds. And the idea here is to investigate the logarithm of the factorial versus something which can be thought of as like an average of the lower and upper bound. So here we have log n, here we have log n plus 1, and for large n, if we deal with this term as log n, then here we have n, here we have n plus 1, and their average is n plus 1/2. So again, inspired by this like sort of of loose bounding on the factorial of n, we can basically focus on constructing a bound using this n plus half all times log n minus n. And specifically, we will study the difference between these two guys, the discrepancy between log of the factorial of n and n plus half log n minus n. Okay, and so we will give this a name. So we will define d sub n. So that's a sequence that is log factorial of n minus this term here. And this sequence starts from 1. If we put n equals 1, then log factorial of 1 is 1, log 1 is 0, and then here we have log 1, which is 0, and then we have 1. And then you can insert any n and get a value for this sequence. We are interested in studying, for example, the monotonicity of the sequence, or of a related sequence, as we will see. So to study monotonicity, what we will do is that we will basically write down an expression for dn plus 1 by taking this expression and replacing every n by n plus 1. So this n becomes n plus 1, and here also we'll do the same. So this will be dn plus 1. Now, n plus 1 factorial, this is log n plus 1 times the factorial of n. And so this is log n plus 1 plus log factorial of n. So we can, again, take this guy and separate it into a log of the factorial of n. And then there will be a term which is log n plus 1. And so log n plus 1, it's multiplied here by 1, and then there is a term here log n plus 1, and there is a minus n minus 3 over 2. So we can take this term and combine it with this one here to have minus between brackets n plus half log n plus 1. Now take the difference. Okay, so dn minus dn plus 1. So after doing this step here, we have cancellation. So this will go with this, and there is an n here, and there is an n there. So that's nice. And we end up just with n plus 1 half. So we get, when we do the subtraction, we get here n plus 1 half log n plus 1, and then from here minus log n. Okay, so this was originally n plus 1 half log n plus 1 minus log n. And so these two guys can be combined as log n plus 1 over n minus 1. The one came from, replacing this n by n plus 1. And then when we took the difference, this plus 1 became minus 1. Okay. Now the trick is that we will write this expression here in terms of 2n plus 1. So we will take every function of n that we see here and make it 2n plus 1. So outside, if we take 2 as a common denominator, then we have 2n plus 1 here. Good. And then this ratio, which is n plus 1 over n, can be written as 1 plus 1 over 2n plus 1 over 1 minus 1 over 2n plus 1. And we can basically verify this. If we take 2n plus 1 common, then here we will have 2n plus 1 plus 1. And in the denominator, we will have 2n plus 1 minus 1. So this will go with that. And then in the numerator, we have 2n plus 2. So that's 2 times n plus 1. And in the denominator, we will get 2n. So 2 will go with 2. And we are left with n plus 1 over n. So now, as we can see, that we can take, the n's that, that appear here and express everything using 2n plus 1. This is clear in the pre-log factor, and this n plus 1 over n, again, it can be nicely written as 1 plus 1 over 2n plus 1 over 1 minus 1 over 2n plus 1. And now let's define a variable u. So u is the reciprocal of 2n plus 1. So the outside factor here will be 1 over 2u, and then those guys here will be log 1 plus u over 1 minus u, which can be written as the difference log 1 plus u minus log 1 minus u. And the minus 1 remains intact. Okay, now the next step is to try to basically deal with these logarithms, and specifically we will go for the Taylor series. We have Taylor series expansions for expressions like log 1 plus z or minus log 1 minus z using these sums here, and those are valid so they are valid for a general complex valued z, so long as the magnitude of z is strictly less than 1. And we are okay here. We have no problem because basically u is 2n plus 1. So basically the highest possible value of u is 1 over 3. So no problem. So we can expand those logarithms and write them using their Taylor series expansions. And now, if we look at the sums, they look nice. They will differ, you know, in one summation. The summation with this plus will give us this alternating 1 minus 1, 1 minus 1 factor. But this guy, it does not have those terms here. And so we will find that the two sums actually, if j is even, if the index of summation j is even, then j minus 1 is odd. And we will have a minus sign here, and the terms will cancel. So the even terms in these two integrals, these two convergent, sums in these two convergent sums will cancel, and the only survivors will be the odd terms when the index of summation j is odd. Okay, so in that case, the two terms here will be exactly the same. So now we can basically combine these two sums and have a summation j from 1 to infinity, and we will replace j by 2j minus 1 to say that basically the odd terms are combined together, and the even terms cancel because of this factor of minus 1 to the j minus 1. Now, the first term in this summation, the first term is u to the 0, which is 1 over 1. So the first term in this summation is 1. We have a minus 1, so we can just eliminate the first term, and now we have a summation that starts from j equal to 2. Okay, so this is the summation that describes the difference between dn and dn plus 1. And don't forget that dn is a study of this difference or discrepancy between the logarithm of the factorial of n and this term, which we hope to play a role in, like constructing a tight upper bound and a tight lower bound on the factorial of n. Okay, now from here let's basically do bounding. So this is a summation, and it is clear from this summation that it is a summation of non-negative terms. Okay, so this is a summation of non-negative terms. And so this means that dn minus dn plus 1 is something that is positive. Okay, so we can make a conclusion here that if our interest is the sequence dn, then sequence dn, where n is a strictly positive integer, this sequence is decreasing. It is strictly decreasing, right? Because it's always the case that dn is superior to dn plus 1. The difference between the two guys is strictly positive. So the sequence dn itself is a decreasing sequence. So keep this in mind, but we will try to do something else. Can we upper bound this difference? Well, the difference is given by this summation. In the summation, we have the powers of u. So if we just have the powers of u, then we have a geometric series. But we also have this denominator. But we can do something. We can basically upper bound by replacing all those terms here, 2j minus 1, by the smallest value. So when j is equal to 2, the denominator here, 2j minus 1, is equal to 3. So 2j minus 1 is less than or equal to 1/3 for j greater than or equal to 2. And by doing this, we now obtain a geometric series. And it is a converging geometric series. So we can just do the sum. And here is what we get when we use the relationship between u and 2n plus 1. U is the reciprocal of 2n plus 1. And we will get that basically this upper bound is 1 over 12 n plus 1. And 1 over n plus 1 can be written as 1 over n minus 1 over n plus 1. So this is a very nice upper bound on the difference dn minus dn plus 1. And the reason for this is that we have a term that depends on n and another term that depends on n plus 1. And so what we can do is that we can take this guy with dn, okay, and then we can take this guy to the other side, and both of them, they are indexed by n plus 1. So we have that dn minus 1 over 12n is strictly less than dn plus 1 minus 1 over 12n plus 1. So we can think of this as a sequence now. not just dn minus 1 over 12n. And this is the next term in the sequence. And what is happening in this sequence? If we increase n from n to n plus 1, basically the sequence increases. So the sequence dn minus 1 over 12n is strictly increasing. That's a strictly increasing sequence. Okay. So let's go back to dn minus dn plus 1, and it is given by this summation. And don't forget that this summation, it came from basically writing things in terms of the logarithm and then taking the Taylor series expansion. So now we have this summation. Now let's have a bound on the other, in the other direction. So the first step we upper bounded. Now let's lower bound. And if we have a summation of non-negative terms, then we can lower bound by keeping one of the terms. Okay, so this is exactly what we'll do. So the difference is this summation. We will just keep the term corresponding to j equal to 2. So this will be u squared divided by 3. So this is a lower bound on dn minus dn plus 1. That's lower bound. And if we replace u by it is the reciprocal of 2n plus 1, so this is what we get. So we will get 1 over 3 and then 2n plus 1 squared. Now we will do a further step of lower bounding. It can be done in a number of ways. So for example, here I multiplied and divided by 12. Okay, and basically this lower bound that we have obtained can further be lower bounded by this. Okay, and so basically the idea here is when we had the upper bound, we got those nice terms that dn minus 1 over 12n is a sequence, and it is a strictly increasing sequence. So we are trying to basically have something that looks like this. So this is the motivation to modify this lower bound by saying that this term here is strictly greater than this term here. Okay, and this is 12n plus 1, and this is 12n plus 13. So 12n plus 13 can be written as 12n plus 1, 12 open bracket n plus 1 and then plus 1, and then these two guys can be these two brackets can be separated as this difference. You can just verify, just multiply these two guys, and you will get exactly this quantity, which is again a lower bound on the quantity that we get by keeping just one term in this summation. How do we know that this is less than that? Sorry, this is greater than that. A number of ways. So this is one of them. Pick any strictly positive integer n. It's the case that 24n is greater than 23 because the minimum value of n is 1 and 24 is greater than 23. Okay, and then what you can do is that you can add 144n to both sides. Okay, and in that case, you will get that 168n is greater than 144n plus 23. Then we can add 13 to both sides. Note that here, why I'm doing this, because I want this side, the right-hand side, to look like the expansion of this guy. So that's the lower limit. And when we multiplied upstairs and downstairs by 12, then downstairs we have 144n squared plus 144n plus 30 plus 36. So for example, to change this 23 to 36, you can add 13 and so on. So again, it's basically straightforward, and it can be shown in a number of ways. The idea is to get something like that depends on like 12n because this has already appeared in the previous bounding step. Now, I can, this depends on n. Here we have n plus 1. We can move this guy and stick it to dn. and then we can move this minus dn plus 1 and move it to this guy where we have n plus 1 here. So we have this relationship. dn minus 1 over 12n plus 1 is strictly greater than dn plus 1 minus 1 over 12n plus 1 plus 1. And so we can think of this as a sequence indexed by n. And now if we go from small n to small n plus 1, what will happen is that the sequence will go down. So the sequence dn minus 1 over 12n plus 1 is strictly decreasing sequence. So now we have two conclusions by investigating this sequence d of n. The dn minus 1 over 12n is strictly increasing. It is a strictly increasing sequence. And dn minus 1 over 12n plus 1, this is a strictly decreasing sequence. And of course we have, because 1 over 12n plus 1, this term here alone is less than 1 over 12n, because we have a larger number in the denominator, then with a minus sign, this will be greater. And so dn minus 1 over 12n plus 1, this is always superior to dn minus 1 over 12n. Note that the sequence that we have on the left-hand side, this sequence is strictly decreasing. And this one that we have on the right-hand side is strictly increasing. Both sequences are strictly monotonic. Note that for every n, this inequality is true. And this sequence on the right-hand side is strictly increasing. Its minimum is when small n is equal to 1. And so the minimum value here is d1 minus 1 over 12 times 1. And d1 is equal to 1. And so basically the minimum is 11 over 12. So now from the point of view of this sequence on the right-hand side, this is a sequence that is strictly decreasing. And now it is bounded below. So this sequence is greater than this. And this is a strictly increasing sequence. And it is always greater than or equal to d1 minus 1 over 12. So this is the smallest guy in this sequence. And it will happen when small n is equal to 1, because this sequence is strictly increasing. So d1 minus 1 over 12, which is 1 minus 1 over 12, which is 11 over 12, is a lower bound on this sequence. So this sequence is monotonically decreasing, it is strictly decreasing, and it is bounded below. So by the monotone convergence theorem, for sequences, this sequence converges. Also from the point of view of this sequence is strictly increasing, and it is upper bounded by this sequence, which is strictly decreasing. So the maximum value of this sequence happens when the index n is equal to 1. So this is less than or equal to d1 minus 1 over 12 times 1 plus 1. So d1 is 1, and so basically the maximum value here is 1 minus 1 over 13, which is 12 over 13. So the sequence here is strictly increasing, and it is bounded from above. Okay, so both sequences, by the monotone convergence theorem for sequences, they converge. And note that each of those sequences is a term that is guaranteed to converge. We don't have any doubts about it. So those two guys, both of them converge to 0 as n goes to infinity. So now we reach the conclusion, it must be the case that the sequence dn converges. So sequence dn must converge. The limit exists as n goes to infinity. And let's give this limit a name. Let's call it C. Okay, so our study of the monotonicity of the sequence dn, it paid off. Okay, so we discovered that we have an increasing and a decreasing sequence, strictly decreasing sequence, strictly increasing sequence, and they bound one another, and so we have convergence and there is a limit for the sequence dn, and this limit is c, and it is not clear. It is not clear what the value of c is. Right, so based on our bounding arguments, like dn, the sequence dn is living between 11 over 12 and 12 over 13. But what is the limit exactly? We don't know. For now, we don't know. But suppose that you know c. If you know c, so c is basically the limit of this strictly decreasing sequence. Okay, so c is less than or equal to this term here for every positive integer small n, and c is the limit of this strictly increasing sequence. So c is this mysterious number that is living between these two guys. So this inequality, which is like written in such a way that c is bounded, it can be easily modified so that we have dn in between, right? So if we move this term to the other side, then we have c plus 1 over 12n plus 1 is less than dn. And then focusing on this side, dn itself is less than c plus 1 over 12n. Now, go back to dn. Here is its expression. So it is the logarithm of the factorial of n minus those guys. Put it here in between those bounds that involve c, and you get this. Now, exponentiate the three sides, okay, and so you will get this here. So here we have e to the c times e to the 1 over 12n plus 1. Note that this is a term from the very beginning. This is a term that appears here in the lower bound of Stirling's approximation. So we are close, but it is still annoying that we have no idea what c is. But at least if we imagine that we know c, that you have this is less than a factorial. So when we exponentiate this, we will get e to the log the factorial of n. So that's the factorial of n, and then we will get e to the n, and then we'll get 1 over n to the power n plus 1/2, which is 1 over square root n to the n. And then those guys can be moved to the other side. So we can basically multiply all sides by square root n to the n divided by e to the n, and then we have bounds for the factorial of n. Now those bounds are they have this constant that we are sure by the monotone convergence theorem for sequences that this constant exists. It's a number, but we still don't know what this number exactly is. So the remaining part of this adventure is simply to obtain C. If we obtain C, then we are done. So to obtain C, we will basically do a derivation here, which is the Wallis product. Okay. So this is simply a certain limit that involves factorials, and it will involve also pi, as we will see. And it is that limit that will allow us to compute C. So our hero here is this integral. Okay, so we'll define integral in, where n now is a non-negative integer, so n can be 0, 1, 2, and so on. And this is the integral of the nth power of sine from 0 to pi. Now, if n is equal to 0, then the integrand is equal to 1, and the integral is pi. If small n is 1, then we are integrating sine from 0 to pi. So the integral of sine is minus cosine, and so we can put cosine and switch the limits. So this will be 1 minus minus 1, which is 2. So we can easily compute those integrals for n equals 0 and for n equals 1. What if n is an integer that is greater than or equal to 2? In this case, let's do one step of integration by parts. So when we do this, we will get a term here which is sine to the n minus 1x. Now, if n is 2 or more, then we have here sine x or sine squared or sine cubed and so on. And sine of 0 is 0. Sine of pi is 0. And so this term will disappear whenever n is greater than or equal to 2. And then when we do the integration by parts, we will have a cosine. And then when we differentiate, so we'll have a cosine. And then when we differentiate this guy, we will get n minus 1 sine to the n minus 2 of x. And then by the chain rule, we need also to differentiate with respect to the sine. So these two cosines will give cosine squared, and then we have n minus 1, and then we have sine to the n minus 2x dx. Okay. Now take this cosine squared and rewrite it as 1 minus sine squared x. Okay, and so again, we are trying to do things in sine so that we relate what we have obtained on the right-hand side to the integral I of n. So if we do this, replace cosine squared x by 1 minus sine squared x, we will basically have an integral, so 1, and then we have sine to the n minus 2x dx. So that's I n minus 2. And then we will have an integral sine squared x times sine to the n minus 2x. That's the integral of sine of x raised to the nth power. That's the original integral, which is I of n, and it's multiplied by this factor n minus 1 that we obtain when we differentiate sine to the n minus 1 x. So this term can be moved to the other side. So the other side we have 1. So now we have 1 plus n minus 1, that's n. So now we have n I of n, and we will have n minus 1 times the integral I n minus 2. So this is a recursive relation, and this recursive relation is very nice. It tells you that, you know, if you know I of 0, and we know I of 0 is equal to pi, then you can obtain I2, I sub 2, you know, basically what will happen if you are integrating sine squared, I4, I6, and so on. Now, if you know I1, and we do know I1, it is equal to 2, then we can obtain I3, I5, I7, and so on and so forth. Okay, so the ratio between In and In minus 2 is n minus 1 over n. And as you know here, because like I0 is pi, I1 is 2, then like we need like to handle the two cases separately. What if n is even? So here we are replacing n by 2m, and here we are replacing n by 2. We're replacing n by 2m plus 1. Okay. So here are the cases in which n is equal to 3 and 5 and 7 and so on. And here are the cases in which n is equal to 2 and 4 and so on. 0 and 1 are already handled separately. Okay. So again, as I said, that this recursive relation will allow us to write, so if you know I of 0, which is pi, then I2 is basically this factor with m set to 1 multiplied by I of 0, which is equal to pi. So we'll discover that I2 is pi over 2. Now, if we put small m equal to 2, then we can relate I4 to I2. And then since we know I2, then I4 is 3 pi over 8 and so on. And so generally, I, and the index is an even integer. So so basically starting from 2, so basically I2, I4 and so on. So this will be 2m minus 1 over 2m, and then we reduce the index m by 1, and then we reduce it again all the way to putting small m equal to 1, and this will give us 1/2, and then we multiply by I0, and I0 is equal to pi. Okay, so this is an expression for the value of our hero integral, so long as we are integrating an even power of the sine. Now we can leave those guys multiplied, and this will be a product. But for our purposes here, we will try actually to write down those products in a form that will serve our purpose. Remember that we want to bound factorial. Okay, and so if we look at the denominator, we have those terms 2m, 2m minus 1, 2m minus 2, and so on. And so in the denominator we have m2's multiplied together. That's 2 to the m. And then we have m minus 1, m minus 2, all the way to 2 by 1. So that's factorial. That's the factorial of m. Now in the numerator, we have a double factorial, because we have 2m minus 1, and then 2m minus 3, and then 2m minus 5, and so on. But what we can do is that we can insert 2 and then 4, and then, all the way to 2m minus 4, 2m minus 2, and 2m. So that in the numerator now, we have the factorial of 2m. And of course, we need to divide by those terms that that were not there upstairs in the numerator. So we need to divide by 2 to the m, and then m factorial, because those guys we can take, from each one of those guys we can take a factor of 2. We have m terms, so we have 2 to the m, and then the remaining guys will be m by m minus 1 by m minus 2 and so on. That's factorial m. And so we need to have this guy in the denominator. Okay, so we have now this expression for I to m. Now we will repeat the exact same story for for in, where n is an odd integer. So I1 is done. I1 is equal to 2, and again we can express I3 in terms of I1, and sorry, this should be I5. Okay, and we can have I5 in terms of I3, which is expressed in terms of I1. So again, we can do exactly the same thing, that I to m plus 1, and we take this expression here, and write 2m over 2m plus 1, and then we reduce the index by 1, then we reduce the index by 2, and so on, all the way to this term here, when small m is equal to 1. This will give us 2/3, 2 over 3. And then this 2 here is I1. As we have done for I with a subscript 2m, we can take the terms in the numerator and denominator and express them in terms of factorials. Now, sine x is a number between 0 and 1, when x is between 0 and pi. And so sine x raised to the power 2n minus 1 is greater than or equal to sine x raised to a higher power, which is 2n, which in turn is greater than or equal to sine x raised to the power 2n plus 1. So this again, because sine x is a number between 0 and 1. Now, if we take this inequality, integrate all sides from 0 to pi, then we get an inequality relating our integrals. So I to n minus 1 is greater than or equal to I to n, which is greater than or equal to I to n plus 1. We have expressions for each one of those integrals. So we can take those expressions and put them here. And then we can basically manipulate the terms and do some rearrangements, and we get this nice inequality here. So this quantity, which involves the factorials of 2n and n, this is less than or equal to 1. And on the other hand, it is greater than or equal to 2n over 2n plus 1. Note that this will tend to unity, to 1, as n tends to infinity. So we can do this, or we can first take the square root, and if we take the square root and then take the limit as n tends to infinity, this is a constant sequence of 1s, so the limit is 1, and this will tend to 1 as n tends to infinity. So by the sandwich or squeeze theorem, it must be the case that this quantity here tends to 1 as n tends to infinity. So using again this idea, we were able to obtain a limit. Okay, we obtain this limit result here, that the limit as n tends to infinity, factorial of 2 times square root of n over 2 to the 2n, and here in the denominator we also have the square of the factorial of n. This quantity here, if we multiply by square root of pi, then it tends to 1 as n tends to infinity. This will be our way to determine the constant c. So remember, we had this sequence dn, and we proved that the sequence dn is convergent, and the limit value is c. We wrote down, upper and lower bounds on the factorial of n in terms of this c. Now it's time to obtain this c by exploiting basically the limit result that we have here. So because our limit, it involves the factorial of 2n and a factorial of n squared, then we can use our bound. For example, if we replace n by 2n, then we can have upper and lower bounds on the factorial of 2n. If we if we basically take the reciprocal of all sides, and of course will change the inequalities, and then square, then we can have upper and lower bounds on 1 over the factorial of n squared, and then we can multiply. After doing this, we will get those lower and upper bounds on this quantity here. Then the lower and upper bounds, they involve e to the c. We get e to the c because our bound involved e to the c. When we wrote down the bound for the factorial of 2n, e to the c is left intact. But when we have the upper bound on 1 over the factorial of n squared, so because we square, then we will get e to the 2c. So when we multiply, we have a survivor term that includes this constant c that we are after. Now, let's rewrite this inequality. We will multiply all sides by e to the c, and then by the factorial of n squared, and then we divide by the factorial of 2n. So when we do this, the middle term here will be changed to e to the c. And then, now the lower bound and the upper bound are free from this constant c. So now we have an inequality, and this inequality is true for every positive integer n. So this is true for every n, no matter how large. In other words, we can just, take the limit of all sides as n goes to infinity. This is a constant, which is e to the c. Now, what will happen to both sides in the limit as n tends to infinity? We have those scary looking exponentials, but they are as innocent as it can get. Simply when n gets very large, those guys will converge to 0. Their difference will be 0. E to the 0 is 1. So basically, the exponentials that we have here on the left and right hand sides, they will converge to unity as n tends to infinity. And then we have those square root 2s. What about those guys? Those are basically the terms that appear in this limit result. So that's it. We will discover that actually the left-hand side and the right-hand side, they both converge to the exact same limit as n tends to infinity, which is square root 2 times square root pi, or square root 2 pi. Okay, and so this is the value of e to the power c. Okay, so c itself is the logarithm of square root 2 pi. Okay, and our bounds on the factorial of n, they involve e to the c, so we can just replace this e to the c here and there by the square root of 2 pi, and now we have basically the bounds, the desired bounds on the factorial of